Hello warriors, this is Miss Lemons, and today we are going to be going over the stoichiometry BCA tables cheat sheet. So this was a handout that you should have received. You're going to end up putting it into your packets if it's not already there. All right, so let's just get started. First things first, what unit belongs inside a BCA table? And the answer to this is only moles. Moles only, forever and ever and ever. If you put anything else other than moles inside this table, you're going to have a bad day. So please make sure that whenever you are converting, for instance, if you are given grams, then you need to convert to moles. If you are given particles, you need to convert to moles. If you are given molarity, guess what, guys? Convert to moles. If you are even given volume, which is liters, convert to moles, folks. So the only way that you are able to use this table is if you have moles. Once you have moles, then you're good to go. All right, so let's go ahead and just start with this practice problem. There's a few tricks that I want to teach you, and a lot of it is, hey, what can we do to not do math? Because this is a unit that is based entirely in math, and so it's important that we can avoid math for as long as possible if we're uncomfortable, and then after we filled in as much as we can, then we can do math, okay? So let's take a look at this problem that we have here. Everything in stoichiometry is going to be in the form of a word problem. So it's important that we're paying attention to these word problems with a really good analytical eye. We're reading these and we're annotating them. So number one here, it says a combination reaction occurs between solid magnesium metal and diatomic gas, oxygen gas. Solid magnesium oxide is produced. Cool, that just described the reaction to us. It's already down here for us balanced. So it says 17.54 moles of solid magnesium reacts completely with excess oxygen gas. Use the mole ratios to complete the BCA table. Okay, so some key words here. First off, we have a number. Numbers are important, right? So this number is talking about solid magnesium. Okay, another thing about solid magnesium is that it's reacting completely, reacts completely. This is important. What this means is that when something reacts completely, we'll write it down here, reacts completely, that means that we are going to use up all of that solid magnesium. Okay, so I'm going to go ahead and make that a little bit smaller. So keyword number one, if we see reacts completely, that means we are using up all of the substance. Okay, so it also says that we are reacting with excess oxygen gas. Okay, when we see excess, that means two things. One, we're going to start with an excess of oxygen gas, and two, we're going to end with an excess of oxygen gas. So an excess means that we will begin, or before, we will begin the reaction with an infinite amount of gas, which means we will also end the reaction with an infinite amount of gas. All right, so now that we have our little disclaimers here, some guidance to those words, now we can go ahead and start filling things in. Now, when I fill out my BCA table, I like to use this top row here to fill in essentially my balanced chemical equation with the coefficients. So we're going to go ahead and do that. I'm just going to essentially copy paste each one of these and plop it into the BCA table below. And this is a good habit for you guys to get into, is to just copy down each of those reactants and products into your BCA table the way that they're written with their coefficients, so that we don't lose sight of what the coefficient or that mole ratio is. All right, great. So now that I have that done, I also like to do a little, I like to separate everything to make it look really obvious that we are in fact working with a chemical equation, and then I don't lose sight of where my products and reactants are. Okay, so here I've got my plus symbol, and then I've got my arrow. Great. Okay, so now this is going to help me stay on track. Just as a reminder, the stuff that we have over on the left-hand side is going to be your reactants, and the stuff on the right-hand side is going to be your products. All right, so let's start filling in the numbers of the table, the meat and potatoes of the table. But in order for us to do that, we really need to understand what each of these letters stands for. Before, or is our B, so before. The C stands for chemistry, and the A stands for after. Right. And we're talking about what's happening before the chemical reaction versus after the chemical reaction. So before the chemical reaction even begins, this is where we're going to start looking at what was given to us in the written problem. It says here that we are starting with 17.54 moles of solid magnesium. Okay, so I can use that information. We are starting with 17.54 moles. Make that a little darker here. There we go. And it says we're reacting it to completion, which means that I'm going to use all 17.54 moles. More on this detail later, okay? We also know that we are working with an excess of oxygen gas. That's what we're starting with. So we are going to write excess for oxygen. And if we have an excess amount of gas, that means we're going to end with an excess amount of gas. So after the chemical reaction takes place, we will end with an excess amount of oxygen gas. So now we have to figure out what the heck we're going to do for MgO, magnesium oxide. Now, the cool thing about this is that because magnesium oxide is a product, we actually don't start with any product. Like, you don't have a PB&J sandwich before you make the PB&J sandwich. You don't have magnesium oxide before you make magnesium oxide. So the cool thing about products, one of our little tips for the before square, is that whenever you have products in the before column, they will always be 0 moles, because we always start with 0 products. So products will always start with 0 moles in the before row. Fabulous. Now, let's go ahead and kind of move on to the next row, because we've already filled out all of the before row and I haven't done any math yet. So now on to the chemistry row. Now, it's important to know that when we're talking about chemistry, we are talking about the action of producing a chemical reaction. The chemical reaction is taking place. This is like the action row. Okay, so a few memory tricks to remember what on earth are we supposed to do with this row. You could say that C stands for chemistry, but you could also say that it stands for calculating using the coefficients in a conversion factor. And just so you know, that conversion factor that we're going to be using is going to be the mole ratio. So that would be the number of moles of X for the number of moles of Y. This is our mole ratio that this is the conversion factor that we are going to be using. And it depends on what we are working with as far as which numbers go in there. But those numbers are the coefficients from the chemical equation. So we use this mole ratio to help us calculate these other two boxes in row C. So in row C, we are doing some sort of math. We're going to skip row C for right now, and we're going to move down to row B to see if we can fill out anything without doing much math at all. For instance, this first column. We already know that we're starting with 17.54, and according to this word problem, we are going to be using all of that substance, which means we are going to be left with 0 moles of that substance. So the cool thing about this is that we are just mathematically combining rows B and C to figure out A. So as long as we're able to fill out rows B and C, row A is simple subtraction or addition problems. So it's also important to know that you are not going to always end up with 0 moles in your reactants. It just so happens to work that way here. All right, again, the amount of math we've done, very minimal. Let's move on to my next favorite to fill in is this C column right here. Now, the reason why I'm pointing to this one for magnesium oxide is because it has a 1-to-1 ratio, 2-to-2 ratio with magnesium. That means if we have 2 moles of magnesium, we're going to make 2 moles of magnesium oxide. If we have 8 moles of magnesium, that means we're going to have 8 moles of magnesium oxide. If we have 42 billion moles of magnesium, we're going to have 42 billion moles of magnesium oxide. So if we have 17.54 moles of magnesium, that means we're going to have 17.54 moles of magnesium oxide. Again, I just understood the 1-to-1 ratio. I didn't really have to do any math at this point. So let's go ahead and add that. Now, you might have also noticed that I added this plus symbol, and there's a minus symbol here. And I mentioned the minus symbol a little bit earlier, but let's go ahead and write a little blurb about what the heck that even means. You see, chemistry column or the chemistry row is when we're actively doing chemistry. We are either using up reactants or making products. So the negative symbol means we are using reactants. The plus means we are making products. You will never see a plus sign over on the reactant side, nor will you ever see a minus symbol on the product side. All right, so now that we know what the symbols for row C are, we can go ahead and fill out this bottom corner. Again, for row A, we are mathematically combining rows B and C to figure out row A. And here, we're just adding 17.54 moles to 0. It's like an addition problem. We just draw a line underneath this and do vertical addition. So we are now going to end with 17.54 moles of MgO. Now notice that I didn't put the plus symbol there, and that's because we are not actively creating products. We have those products. We already made them, so we're done. So the last thing that we need to do is this box right here in the center. Special thing about this box is that now is the first time we actually have to do dimensional analysis. So as long as you understand how a BCA table works, you understand simple addition and subtraction, and you understand the relationship, that mole ratio between those substances, you actually don't have to do a whole lot of dimensional analysis. So let's go ahead and put together the dimensional analysis to figure out this box. So we are going to use the SUCS method to figure this out. Again, you don't need to do this, nor do you need to actually show your work for this in the future, but we do need to know how we get from point A to point B. So we are trying to figure out moles of oxygen, but we were given moles of magnesium. So we're going to be using what was given to us in the formula. So I have 17.54 moles of magnesium. That is my starting value. All right. Then our unknown is the number of moles of oxygen, right? Because that's what we're trying to figure out here in the chemistry row. And our conversion factor is going to be the mole ratio using the numbers from the coefficients of the chemical equation. So I'll go ahead and type that in. So here's our conversion factor. Notice that it's set up in the same way as our ratio here. That's moles of X for every moles of Y. That is 2 moles of magnesium for every 1 mole of oxygen. And again, I got those values from up here. That 2 to 1 to 2 ratio, 2 moles of magnesium to 1 mole of oxygen. Okay, so now our final step is going to be setting up and solving. Our setup will always be the same. We're starting with what we know over 1. So give me a moment to type that in. So here is our structure. This first fraction is always going to be what we know over 1. So that means we're going to start with what we know, 17.54 moles, and we're going to place it over 1, just like this. My memory trick for dimensional analysis is what's on top must come down. So we need to use our moles of magnesium conversion factor, because that's what this fraction is for. If we already use 1/2 of our conversion factor, we have to use the other half of our conversion factor on top. So we're going to go ahead and plop that on top. Now we're going to go ahead and multiply across the top and across the bottom, then divide the top and bottom of our new fraction to get our final answer for that box. So we're going to take 17.54 times 1 to get 17.54, 1 times 2 to get 2, and then we'll divide the top and bottom to figure out our final answer, which is 8.77 moles of O2. Now, I can take this value, and this is how much we are gaining, or how much we are using in here. And remember, because it's in the C row, we need to pick that symbol. Is it going to be a positive symbol or is it going to be a negative symbol? Well, because this is a reactant, we are actively using it, and so it should be a negative symbol. This is your completed BCA table, and we only had to do dimensional analysis once.